The problem statement of this journal is that the multi-level inventory problem consists of two sub-problems, which is the upstream manufacturing system and the downstream distribution system, where the problem of manufacturing system is that the manufacturer enterprises have clear production, therefore the inventory demand is a main problem. And the problem in distribution system is that the market-oriented inventory demand problem. Next, the paper consider a three-level fresh agriculture product inventory system, which consists of one manufacturer, multiple distributors, multiple retailers, and one supplier. Every node in the system uses the RQ inventory control policy. Lastly, the paper also consider the major costs in the system, including the order cost, storage cost, shortage cost, transportation cost, and good loss cost. Next. And I'll talk about the methodology of this journal. The paper builds a mathematical model of multi-echelon inventory system of fresh agricultural products where there are two assumptions of the models, and these two are the assumption of the models. Next. Then, these are the notations for the mathematical model. Next. There are three different inventory models of the mathematical model, which are the inventory model of retailer, distributor, and manufacturer. Next. Then, this paper also designed a simulation-based optimization approach. It combines the simulation and optimization method together. Then, they use the output of the simulation to guide the optimization algorithm to find the optimal value. So, the output response will constantly improve in the simulation environment. Then, the FlexSim software and improved particle swarm optimization algorithm is also used. Then, the general step of logistics simulation modeling based on FlexSim are divided into system investigation before modeling, model building, data input and realization of simulation logic, model validation, and result output and simulation analysis. And the below flow chart shows the operation flow of the simulation-based optimization approach. And this is my part, and I'll pass to my next teammate. Thank you.
I am Kamchari, and I will give a brief explanation about case study. So this diagram delivers a general idea of multi-echelon inventory system that will be used in agricultural products in a certain chain enterprise. So it consists of one manufacturer, two distributors, and five retailers. And the parameters involved are shown here, which including shortage cost, order cost, transportation cost, loss rate, initial inventory, delay time, demand time interval, and good loss cost. So for your information, shortage costs are different under variety service levels F, and loss rate also depend on the number of storage day. So the higher storage day will lead to the higher loss rate. Next. So how does this simulation-based optimization model establish? We'll first take a look on the layout of simulation model. So basically, this one node on the right-hand side represents manufacturer, and the two nodes represent distributors, and the five nodes over here are retailers, and the dots are customers that will generate random demands for retailers. Then we'll briefly look at the logic flow and parameters setting. So this figure on the left shows the simulation logic flow of the customer side, while the figure on the right shows the simulation logic flow of the supply side. So the running time of this model is set to 4,500 seconds, where 30 seconds are equal to 1 day. So there is 150 days in total. Then the service level F of inventory system is by the difference between the total order quantity and the total order shortage divided by the total order quantity. Besides, the number of particles in the particle swarm is set as 20, and each particle has 16 variables, including order point and order quantity of 5 retailers, 2 distributors, and manufacturer. And then the number of iteration is also set to 100. Next, we'll take a look on the effect of velocity constraint. So k is a constant that will affect the particle velocity, and larger k results in better optimization result. Next.
I'm Jingy and will continue with the part of simulation result. So after running 100 iterations of the simulation-based optimization model to output the inventory cost optimization result, we will get the inventory cost of the initial iterative optimization is 76,608, and the final optimal value is 70,224, which is shown in the graph on the left-hand side. The graph on the right-hand side is the content vs time and average content of each node in the initial policy vs compared with the optimization policy. This result shows that the smaller the value of R and Q, and the more conducive to reduce the inventory. So we can see that the inventory of retailer 1 and 2 in the optimization policy is higher than the initial policy. Then for the other nodes, the optimization policy are less than the initial policy. Then from the table 5, the R and Q value of the optimization policy are less than the initial policy, which also indicate that the good loss quantity of optimization policy is less than the initial policy in table 7. From table 6, the optimization policy has more order compared to initial policy. The order cost of optimization policy is slightly bigger than the initial policies. So by comparing the table 5 and table 6, it is shown that transportation cost of the initial policy is slightly larger than the optimization policies, as the transportation cost of the inventory system depends on the order number and the quantity of order. Next, for the table 8, the shortage quantities of initial policy is slightly less than the optimization policy. So from this result, we can conclude that by reducing the R and Q values, will reduce the inventory, but will also result in an increase in the shortage cost.
So for the discussion part that we are going to talk about is comparative analysis of simulation policy and mathematical policy. We'll divide into two parts, which are retailer and distributors side and manufacturer side. So based on the result we mentioned earlier, RQ policy, total order in each node, quantity of good loss in simulation optimization for retailer and distributors are smaller than mathematical optimization policy. Thus, the cost used in simulation optimization policy for retailers and distributors is lower. On the other hand, simulation optimization policy for manufacturer has higher RQ policy and quantity of good loss and smaller total orders compared to mathematical optimization policy. This lead to lower costs in simulation optimization model for manufacturer side. Next.
So as a conclusion, the simulation-based optimization model of the multi-echelon inventory system for fresh agricultural products was proposed by using the FlexSim simulation software and the improved particle swarm optimization algorithm in this study. The simulation results, the inventory cost obtained by simulation method, which is 70,224, is better than the mathematical method, which is 73,757. Lastly, we can know from the above analysis, the control policy of multi-echelon inventory is a complex problem which is restricted by many factors. And then for our future work in this study, we should consider the effects of the price and the freshness of goods on demand, as the variety of price and the freshness of goods will affect the demands. Besides, minimizing the iterative running time of the simulation optimization model will help to reduce the unnecessary iteration and also will help to save more time.
So this is our task distribution throughout the whole assignment. So, and that's all from us. Thank you for lending us your